Hi, this is Peter with CalcBook, and today we're going to be looking at singly symmetric I-shaped members and specifically looking at beam design. So we are going to be doing this calculation in accordance with AISC Specification Chapter F, and we'll be looking at either Chapter F4 for compact or non-compact webs, and then Chapter F5 for slender webs. And the different limit states or design checks that we're going to be looking at today, right? First, we're obviously going to check for the web slenderness to see which chapter we fall into. And then we'll be looking at compression flange yielding, lateral torsional buckling, compression flange local buckling, and then tension flange yielding. And that is going to be the same for chapter F4 or F5. Okay, so let's look at our problem statement for today. So we are going to be utilizing a crane rail example. This is a pretty common shape for a crane rail where you have a wider top flange than you do bottom flange so that the trolley can roll along the bottom flange. So it's going to be a 20-foot long crane rail, simply supported. Our dead load is going to be 3.5 kips. That's going to be a point load at the mid-span. And then we have a live load, or the crane rating, of 8 kips, so a 4-ton crane rating. And just to note here, right, we're going to kind of do a simplified version of the loading here. There are some very specific requirements about maximum wheel load and impact force in AISC 7. So if you are going to be doing a crane rail design, be sure to look at those impact force requirements and the different load combinations required around that. So we're just going to be simplifying that, though, and just using a dead load and live load as shown. So our beam properties, our section is going to look like it's going to have a 10-inch wide flange that's 3/8 thick, a 6-inch wide bottom flange that's going to be 3/8 thick also. Our total depth is going to be 16 inches, and our web is going to be 0.45 inches. And then at the end, we'll do a quick check of a fixed condition just so you can see how CalcBook addresses negative bending for a shape like this. So let's open up CalcBook and we'll get started on the design. All right, we've got CalcBook open now, so we go ahead and enter into our steel design module. We can select 16th or 15th. The calculations are pretty similar. So we'll go ahead and use 16th edition. We'll select our steel member design, and then we'll look at a steel member. And then for this calculation, we're just going to be looking at flexure design. We could be checking shear as well, but for the purpose of this example, we're just going to look at the flexure design about the major axis. So we can go ahead and start by selecting our shape, right? So this is going to be a custom shape. We're going to go down and select custom wide flange, and then we can start entering in our dimensional properties. So the top flange width is going to be 10 inches with a 3/8 thickness. Our bottom flange width is going to be 6 inches with a 3/8 thickness. Our total depth is 16 inches, and then the thickness of our web is 0.45 inches. This is going to be a built-up section, right, out of steel plate, so we are going to consider this A36 plates. And then if we want to, we can jump in and take a look at the various geometric properties, right, for this shape. So we can calculate the area of section, right, figure out where our neutral axis is, right. It's not going to be the middle because our shape is not symmetric about the strong axis. Our different moments of inertia about each axis, the location of our plastic neutral axis, which we'll need for calculation. And then there's some additional design values, torsional constant, distance between flanges, the self-weight of the beam, the section. So a few other things in there that you might want to take a look at before moving on to the design. So we've got that entered. We are going to be using a beam analysis and our AISC 7 load combinations, so we'll leave those as is. And then we can click over to our beam loading tab. So we are going to enter in 20 feet. That's how long our beam is. It's a simply supported span, and our load is at the middle, so we can go ahead and enter in our analysis location is going to be mid-span at 10 feet. We are going to include the self-weight, right? We've calculated that on the previous page, so we'll go ahead and include that. We have a pinned condition. Our self-weight is already included here, but we're going to add our point load, our dead load, right? So it's going to be 3.5 kips, and that's going to be at 10 feet from the left end. We'll hit save. And then we also need to add in our live load, right? The crane loading is a live load. So we want to go add in our crane loading, which is going to be 8 kips, and that is going to be 10 feet from the left end. And we'll hit save. Okay, so now we can quickly kind of review these graphs, right? Just one thing to keep in mind, right? These graphs are, displayed based on the selection here. So you can look at your LRFD load combinations, or you can switch over to ASD and look at the ASD combinations, and then as well your service loading too for deflection purposes. So for us, right, if we have dead and live, we know that we're going to be controlled by 1.2 dead plus 1.6 live. So we can take a look at that, right? We can look at our shear diagram, our moment diagram. We know it's at the middle there, the maximum. So everything looks about right, so we can keep going on from here. So we are not going to look at deflection. You can check that if you want. It'll show the deflection limits, based on your L over 360 or what have you. But we'll go ahead and just jump over to the flexure design. Okay, so we can go ahead and select our buckling length properties here, right? It's asking for negative and positive, but it will automatically figure out which one is correct based on the loading from the beam. So we'll enter in 20 feet for both. And then it should know here to kind of get rid of one of them. So we are going to just look at our positive bending, right? That's what we're looking at here. We can actually take advantage of the lateral torsional buckling modification factor, CB, right? If we open this tooltip here, it will show us if we have a point load with no bracing, we can use this 1.32 increase. So we'll go ahead and add that in to our design. Okay. On the demand side, right, we don't need to do anything. It's automatically pulling over the demand from the beam loading tables, from the beam loading design tab. And we can go ahead and start looking at our design, right? So let's go ahead and jump into our design here. We're going to be checking for our slender elements. Pop that back open. Right, we want to find out what the limiting slenderness is for the compact flange, right? So we calculate that. There's some other factors that we need as well. And then we're going to go ahead and check our top flange, whether it's compact or non-compact, right? So our top flange is going to be non-compact, right? So it falls in between the compact and non-compact sections. Our bottom flange is going to be compact. And then we want to find out what our web slenderness value is, right? That's what's going to decide whether or not we go into chapter F4 or F5. So there's a couple things here we need to calculate, right? Our yield moment, our plastic flexural strength, then we look at the positive and negative bending, right? And based on those properties, we can figure out what our limiting slenderness is for a compact web during positive bending. And we can figure out from all of this information, right? We click into our check web section here, that our web is going to be compact during positive bending, and then it is also compact during negative bending. So that means that we do fall into this AISC Spec Chapter F4. So we go ahead and open that. All right, we've got a couple items we have to calculate before we dive into the actual capacity sections, classification factor, a few other things that you can look at in here, right? But then we get to the limit states that we talked about earlier. So the first one would be the compression flange yielding. Then we look at our lateral torsional buckling based on our unbraced length, right, of 20 feet. Then we look at our compression flange local buckling. And then finally, our tension flange yielding. Right, and we are controlled, as you can see here, by flange local buckling, right, during positive bending. So that is going to be our limiting positive moment capacity, right? And that's what that FLB stands for, flange local buckling of 183 kip feet, right? And our demand is only 87.6 kip feet, so we have quite a bit of room here in this design. So one other thing while we're here, right, we're just going to take a quick look at the beam loading, right? If we just change this to a fixed condition, right, now we have, negative bending on each end of the beam. And we can change our analysis location to 0, or we can make it 20 feet to look at negative bending. And then when we go back into our flexure design, right, it's going to know now that we're looking at negative bending. So it's going to change it over to the negative bending bracing configuration. And then it will run through the same calculations, right? But now everything's flipped. So we'll be checking still the same limit states, right? Same type of limit states, but the top flange is now going to be in tension, the bottom flange is in compression, and so on. And so it will automatically adjust those properties to calculate that stuff correctly. So that is a singly symmetric I-shaped member in CalcBook. We hope you enjoyed the video. We'd like to offer anyone who's still watching a 25% off discount from your first month subscription of CalcBook. You can use the discount code YTCB2024, and you can use that during your checkout for that 25% discount during the first month of your subscription with CalcBook. So hope you enjoyed the video, and we'll see you next time.